Good morning, Professor Manuel Blum and Professor Lenore Blum. Both of them are eminent computer scientists, and it is a great pleasure to have both of them here. So my name is Chiranjeev, and currently the chair of CS department. So it is my pleasure to welcome the speaker on behalf of the department to this inaugural event of Women in Computing. I would also take this opportunity to welcome my IISc colleagues, students, and guests from India and abroad who have joined us this evening. So Women in Computing series is a part of Golden Jubilee celebrations of the Department of CSA. We are 50 years old and now we are the leading CS department in the country. The department is strongly committed to gender equality and since its inception have produced many eminent women scientists. To cite some recent examples, Professor Hima Bindu is now an assistant professor in Harvard. She was a master's student here a decade ago. Dr. Geeta Manjunath is again a PhD from our department, leads a leading healthcare startup in the country. Dr. Suparna Bhattacharya, a distinguished scientist, was recently inducted as a fellow of International Academy of Engineers. So these are fascinating role models, and in the coming decades, we hope to have more such eminent scientists graduating from our department. So I congratulate my colleagues, Professor Bhavna and Professor Chaya, for organizing and conceptualizing this interesting Women series. It reflects the department's commitment of creating awareness around the issue of gender. So this series aims to celebrate research done by women computer scientists and initiate conversations about diversity. It tries to help understand the issues which will help create a better ecosystem and encourage and support academic and professional opportunities for women in computing. I would thank each one of you for joining us this evening and would request now the organizers, Chaya and Bhavana, to begin the proceedings as they deem fit. So organizers, please take it from here.
Thank you, Chiru. Well, it gives me great pleasure to introduce Professor Lenore Blum. Actually, a very warm welcome also to Professor Manuel Blum. We're really grateful that you joined us too, sir. So thank you very much.
Thank you.
So I can't possibly keep the introductions, short when the speaker is so accomplished, but I'll try to be quick. Professor Lenore Blum is a distinguished career professor emeritus of computer science at Carnegie Mellon University. She's the founding director of Project Olympus, an innovation center that works with faculty and students to bridge the gap between cutting edge university research innovation and economy promoting commercialization for the benefit of communities. And Project Olympus is actually a great example of Professor Blum's determination to make a real difference in the academic community and the world beyond. Professor Blum has served the professional community in numerous capacities, including as president of the Association for Women in Mathematics, an association that she founded. Vice president of the American Mathematical Society. She's a member of, she served as a member of the MIT Mathematics Visiting Committee. She's taught at the University of California at Berkeley, was a senior researcher at the International Computer Science Institute and deputy director of Mathematical Sciences Research Institute, both also in Berkeley. She's currently on the advisory board of the new free online World Quant University, built on the premise that while talent is universally distributed, opportunity is not. Professor Lenore's research, from her early work in model theory and differential fields to her more recent work in developing a theory of computation and complexity over the real numbers, has focused on merging, seemingly unrelated areas, whether it's logic and algebra or mathematics and computer science. The latter work, founding a theory of computation and complexity over continuous domains, forms a theoretical basis for scientific computation. And on the eve of Alan Turing's 100th birthday in June 2012, Professor Blum was plenary speaker at the Turing Centenary celebration at the University of Cambridge, England, showing how a little known paper of Turing's, little known to logicians and computer scientists, is fundamental to this theory. And Professor Blum is currently working on an exciting research project with Professor Manuel Blum and Professor Avram Blum on developing a computer architecture for a conscious AI based on cognitive neuroscience. And I believe that's what she'll be talking about. No introduction of Professor Lenore Blum is complete without mentioning her monumental contributions to the field of women in computing. So I'll just say a few words about that now. Professor Lenore is internationally recognized for her work in increasing the participation of girls and women in science, technology, engineering, and mathematics. She was a founder, as I said before, of the Association for Women in Mathematics and founding co-director of Math Science Network and its Expanding Your Horizons conference for middle and high school girls. At CMU, she founded the Women at SCS program and the CS for HS program, now sponsored worldwide by Google. In 2004, she received the US Presidential Award for Excellence in Science, Mathematics, and Engineering Mentoring. In 2009, she received the Carnegie Science Catalyst Award, recognizing her work targeting high tech talent to promote economic growth in the Pittsburgh region and for increasing the participation of women in computer science. A testimony to all of Professor Lenore's efforts would easily be captured by the fact that currently half the computer science undergraduate majors at CMU are women. Phenomenal contribution, and this is just something that other universities can only hope for at this point, but hopefully we'll get there. So when Shaya and I were conceptualizing this whole Women in Computing program, we didn't just want Professor Lenore to give a talk. We wanted her to give the first talk because I don't think anybody else has done as much for women in computing as Professor Lenore Blum has. So on to you, ma'am.
Okay, so thank you, Professor Bhavana and Chaya, professors. It's a delight for me to be here. So I want to say hello from Pittsburgh, Pennsylvania, where I am. And as if you can see from my title screen, I view this as a celebration of women in computing, and particularly that your university has such a increasing percentage of women, successful women in computer science is fantastic. So thank you so much for inviting me and for having me kickstart your hopefully year-long event, more than year-long event, and I know this is part of your Golden Jubilee. Okay. So my title of my talk is What Can Theoretical Computer Science Contribute to the Discussion of Consciousness? And let's see, and here are the three authors. So it's a family affair, this research. And Manuel has been has had a long-term interest in the brain. Avram is an expert in machine learning. And as I understand, he was there 1 year ago helping you celebrate your Golden Jubilee. And here am I. Actually, this picture was taken a few years ago at Carnegie Mellon, and I've been interested in non-standard models of computation. So what do I mean? What do we mean by consciousness? And roughly speaking, by consciousness or conscious awareness, I mean everything you pay attention to, awake or dreaming, but not dreamless sleep. It's what you see, what you hear, what you feel, what you smell, what you taste, your joys, fears, sorrows, and pains, and most especially your own inner private speech. It's your sense of self. And I would say that, first of all, this is admittedly a Western concept of consciousness, but this is by definition what we're looking at today. So until about 30 years ago, the scientific study of consciousness was taboo. And then in 1988, cognitive neuroscientist Bernard Bars published his cognitive theory of consciousness called the global workspace theory. And then in the 1990s, with the advent of fMRI technologies, when neuroscientists could look into the brain and watch what people might be thinking at that time, those two events really helped start the scientific study of consciousness. Then in 1995, I think I hear some other people in the background, maybe you should mute yourself. Okay. 1995, a Nobel laureate Francis Crick talked about the possibility of looking at neural correlates for consciousness. So over the millennia, of course, there have been various approaches to the study of consciousness, going back to Buddha, Confucius, and Plato. Actually, when I was looking at some of the history here, what's very interesting to me is that these three folks who've been very influential in Western and Eastern philosophy actually lived only about 75 years between them. I think Buddha first, and then Confucius, and then Plato, which is very interesting that this whole kind of, I think this very often happens when ideas happen, good ideas happen, they often happen at the same time, more or less, all around the world. Today, there are many, many philosophers looking at consciousness, and I mentioned two, Charles Dennett and David Chalmers, because they represent two sides of the spectrum of thinking about consciousness. One is a functional perspective, and the other is a phenomenological perspective. Of course, the psychological theory in the West started about a century or more ago with William James and Sigmund Freud. And as I mentioned, neurocorrelates, that's Francis Crick, and he worked with Christoph Koch, who's very well known in the area now, on neural oscillations and spikes, looking at those correlates. There's more of a mathematical theory of measures of consciousness due to Giulio Tononi and Koch, and they have a theory called integrative information theory. It's sort of based on Shannon information theory, which gives axioms for consciousness, and a measure phi, which somehow measures the amount of feedback in a system. So those are measures of consciousness. The group that we follow, more of the cognitive neuroscientists, Bernard Bars, Stanislaw Dehaene, and Alan Baddeley, and their work was in turn influenced by a lot of work on cognition, which happened actually at Carnegie Mellon. Yeah, Alan Newell, I think I'm getting some feedback here. Alan Newell, Herb Simon, Raj Reddy, and John Anderson, who took an architectural approach to cognition. And that's sort of the approach we're taking to consciousness. We say it's the architecture that matters. Okay, so what can mathematics or theoretical computer science contribute to the discussion of consciousness? Well, also, we too want to understand consciousness. We want to give a simple mathematical model to help get this understanding. We want to give a good definition of chunk. And in 1950, the psychologist George Miller talked about the magic number 7 plus or minus 2. And basically what he's saying is that's the amount of information that one can keep in the short-term memory at any moment in time. So what's a chunk? It could be a byte, a word, a digit, a poem, where you heard the first phrase and then the next phrase, and then the whole poem will come out. And what we'd like to do is to give a formal definition for this informal notion of chunk. We want to distinguish between simulating and experiencing. We want properties of consciousness to be emergent, not programmed in. We are not looking for a model of the brain, nor of learning or cognition. We are looking for a model of consciousness. We're looking for simplicity, not complexity. And we also, of course, want to give a blueprint for building a conscious-like machine. And currently, this is under construction by our colleague, Jean-Louis Villacroze. In 1995, the philosopher David Chalmers posed these two ways of looking at consciousness. He talks about the easy problems. The easy problems of consciousness are those that seem directly susceptible to the standard models, methods of cognitive science, whereby a phenomenon is explained in terms of computational or neural mechanisms. And this is often called functional or access consciousness. But on the other hand, the really hard problem of consciousness is the problem of experience. When we think and perceive, there is a whir of information processing, and there's also a subjective aspect that's phenomenal, consciousness. Usually this is associated with the word qualia, the feeling of what it is like, and the feeling of what it is like to be a bat, for example. And many focus on what it feels like when you see red. And depending upon where I show this red, east, west, people have different feelings when they see red. In our formulation, we say the easy problem of consciousness is to make a robot that simulates feelings, for example, of pain and joy. And the hard problem is to make a robot that truly experiences feeling, for example, of pain and joy. And you probably have seen Sophia here, who simulates many emotions, and she ends up with an expression of pure pleasure or joy. But although Sophia's expressions may simulate pleasure, she has what we would call acute anhedonia. Philosophers might say she's a zombie. And in humans, anhedonia is the reduced ability to experience pleasure, and it's often caused by a damage to the nucleus accumbens. There are also robots that simulate pain, and if you go to YouTube, you will see this one, and who appears to be in such excruciating pain that it's really excruciating to even watch, and I'm not going to show it to you. But this robot has what we call pain asymbolia, which in humans is a condition in which pain is experienced without unpleasantness. So we don't believe those two robots, though they look like they have pleasure and pain, that they do not experience pleasure or pain. So in our view, consciousness is a property of all properly organized computing systems, whether made of flesh or blood or metal and silicon. Our thesis is that the architecture of these systems is what makes them conscious, and many cognitive neuroscientists agree that consciousness has to do with the architecture of the brain. And the architecture that I'm going to show you explains the brain at a very, very high level of abstraction, a level well above that of neurons. So we will give, and I will give you a formal definition of a machine for consciousness, and we call this the conscious Turing machine or a conscious AI. And then we will define consciousness in that model, then point out properties of consciousness in that model. After all, this is just going to be a definition, so we've got to have to convince you that, in fact, this machine with these properties will have aspects of feelings and the feeling of consciousness. So we are inspired by Turing's simple yet powerful model of a computer that helps give understanding of computation. And as you know, here's a 23-state universal Turing machine that can compute any computable function. So in other words, whatever you can compute in the cloud or in a supercomputer can actually be computed in this little 23-state Turing machine. But you can get your head around a Turing machine, not the cloud, and thus inspired by Turing, we are again aiming at simplicity for our model, not complexity. And our architecture formalizes the theater model or the global workspace model of cognitive neuroscientist Bernard Baars. And Baars describes conscious awareness through a theater analogy. And he says consciousness, again, this is in the concept I'm talking about, is the activity of actors in a play performing on a stage of working or short-term memory. And the inner speech actor is often on stage. Their performance is under observation by a huge audience of unconscious processors in long-term memory that are sitting in the dark. So if I was giving this talk in an auditorium and you, the audience, were sitting there, presumably in the dark, you would be my long-term memory processors, and I would be the short-term memory actor on the stage. Perhaps this is to give you a demonstration of how this might work is you've probably had something like this happen once or twice to you. You're at a party and you see someone you know, but for the life of you, you can't remember her name. But then what happens after a while, you recall where you first met, perhaps maybe in a computer science class that gets in short-term memory and it gets broadcast to your long-term memory processors, your unconscious processors. And then you remember something about what she does that gets broadcast into the cage, into the stage. She's in machine learning, that's her field, that gets broadcast down. And then the processors work down below, and then one processor gets up and says her name begins with a T, and that gets broadcast down. And now, a half hour later, her name comes up to the stage, to the conscious short-term memory from the audience of unconscious processors with thinking, searching. Her name is Tina. The conscious self on stage doesn't know how or where her name was found. The conscious self is not privy to the workings of the unconscious self. And here's a famous example that happened to Henri Poincaré. There are actually quite a few examples like this in the literature. So he's a mathematician who describes that he's been working on a very hard problem day and night. He can't quite crack the nut here. And he's very lucky. He says one day a friend of his asks him to go on a trip with him. And then he says, as I was about to board the bus, the idea came to me without anything in my former thoughts seeming to have paved the way for it, that the transformations I had been using to define the Fuchsian functions were identical to those of non-Euclidean geometry. So what was happening here is that there are two areas of mathematics that he knew very well, and they were in his long-term memory, and the conscious processors were talking together, grappling with this, and then all of a sudden, they come up with that these two ideas, they see the pattern are the same. They're the same. There's an isomorphism between these theories, and that pops up to his consciousness. My students would love to have that happen. Go to sleep, have your ideas in the morning, solve your homework problems. So here's Barr's model of consciousness. At the center, we have working storage, which is his short-term memory, the stage. And down below, we have many long-term memory processors, and this is the audience. To the left, we have inputs from the outside world. This is coming in through sensors for vision, hearing, and touch, and that's going to working or short-term memory. And then on the right, we have outputs to the outside world going through actuators, and that's coming from his working storage short-term memory. And on top here, we have a central executive that might be like a stage manager who's overseeing it all and giving cues and telling people what to do and managing the whole ensemble here. So now let me give you, based on Barr's model, our conscious Turing machine structure. So we start with a tiny short-term memory. It's a read-write memory, very small. And that's our stage. And on stage, an actor can hold one chunk of information. Now, this is not the 7 plus or minus 2 chunks that George Miller says, but through cycling through short-term memory, we could simulate 7 plus or minus 2 if we wish. And after all, since we're looking for simplicity and we can get away with one chunk, we only have one chunk. And then we have the audience of a large collection of unconscious processors. These are our long-term memory processors. They're parallel, they're very powerful, and they start off not connected. They're very independent processors, and there's a huge collection. In fact, we're imagining something like 10 to the 7th processors here, and that sort of correlates with the 10 to the 7th cortical columns in the brain, where a lot of the heavy-duty work is happening in terms of this kind of processing. We also can call this audience, because they're the unconscious, our sleeping experts, and that will come up in a bit. The central executive functions emerge very naturally from our long-term memory processors, and since we are going for simplicity, we do not have a central executive in our conscious Turing machine model. Again, for simplicity, we want very simple. We have a down tree here, and this is from our short-term memory, where the node is down to the leaves, which are in each of the long-term memory processors, and this is for getting information down from short-term memory into long-term memory. We have an up tree, and the up tree here is a binary tree, and it will be the one conducting a competition for our long-term memory experts or sleeping experts to submit their chunks that they want to get onto short-term memory onto stage into a competition. I'll talk about the competition very shortly. We have input, and this is external input. It's read-only. And in our input, we have, it goes from sensors to directly to long-term memory processors. And this is another simplification. These inputs are going directly to the long-term memory processors. They're not going through short-term memory. In fact, short-term memory is just really a holder for one chunk of information. And we don't want things going through it. And whenever I say processor, I will always mean a long-term memory processor. There's a conversion here from worldish, the outside language, maybe of English or Chinese or Hindi, whatever, into the internal language of our CTM, which we call brainish. And again, brainish will be a very important part of the feeling of consciousness in our CTM. So it's the inner language used by the processors in CTM to communicate with each other. It's a multimodal language. So the language can have images, it could have words, it could have sounds, it could have feelings. So it's a multimodal language used to express inner speech, inner vision, and inner sensations. Expressed as multimodal words and phrases called gist, which is richer and more expressive than outer languages. And having an expressive inner language is, again, an important part, as I said, of the feeling of consciousness, and we'll talk about that again. Okay, so we have this external input going directly to long-term memory processors, and we have output going from long-term memory process to the external world. And so this output map will activate actuators that will move limbs or will speak or whatever in the outside world. And in this map, we have a conversion from brainish, the internal language, to worldish, the language of the outside world. Again, we're not going through short-term memory. We're going directly to external output here. Okay, so let me tell you a little bit about the competition. The competition starts when each of the processors puts a chunk into the competition, and we will formally define chunk as a six-tuple. The chunk will have an address. That's the address of the processor that's putting that chunk into competition. If there are 10 to the 7th processors, then the address would be at most a seven-digit address. Then we also have the time that the chunk was put into the competition. The weight is, we have a gist, and the gist is a small bit of information. It's very succinct, it's condensed, multimodal. It's a word or a phrase in brainish, and it can express a query, it can express an answer to a query, it can express, like the query was, what's her name? Might go up, and then an answer to query, I met her in a CS class. And then the weight is the sort of the value or the importance that the processor is giving to that gist. And then we have a few other parameters here, intensity, which starts as the absolute value of the weight, and that's sort of the pressure that the chunk has to get its information into a short-term memory, and the mood, which starts off as the weight. And I have these last two things in red because as the chunk moves up into our competition, the address, time, gist, and weight will stay the same, but the intensities and the mood will change. So here, let me give you an example of very simple competition here. And what we have here is all the processors are putting chunks in, and I'm only giving you 2 of the processors or 3 of the processors here putting their chunks in, and I'm only giving you part of the tuple, the gist, and I'm also giving you the mood that's going up. Everything else will go up as well, but that's all I'm giving you right here. And what's the way, so pain at that point, coming from the pain processor, has a mood of -5, and joy has a mood of +3. And the winner at the local competition right there at that node will be the chunk with the highest absolute value of mood. So here you see that pain has -5, that's 5 is absolute value, it's greater than 3. So pain will move up. It wins the local competition and will move up. But its mood then will be the sum of the moods of pain and joy, -5 + 3, and that will be -2. And that sort of makes sense, even though this is very simple, it makes sense because if you have pain, but you also get some joy in it, that will ameliorate some of the pain going up. And Again, at the next level, we see that fear wins over pain because the absolute value of its mood is larger. And so now fear goes up with a mood of -7. Again, that sort of makes sense that if you have fear and pain at the same time, they will actually maybe increase the fear going up as -7. So this very simple algorithm for our competition sort of makes somewhat sense. And in fact, we don't do anything too much more complicated than that. Our competition algorithms, what they do, they have two parts. Part one computes the local winner of the competition, in this case, the largest absolute value of mood. And part two computes properties of the chunk moving up. So the address, the time, just wait will stay the same. In this case, the mood gets added. And in fact, in this particular algorithm, we'll also add the intensities. So that's this particular simple algorithm. Now, if anybody's been doing a little calculation on the side, you may notice that if we permute some of these processors around, we may get a totally different outcome of what chunk gets into short-term memory. So our probabilistic CTM comes into play at this case, at this time. And this is our preferred model for various reasons. So what the probabilistic is very much like the deterministic model, except at the nodes, we make our decision based on a coin flip neuron. We have coin flip neurons embedded in each of these nodes. And what the coin flip neuron does is it takes two inputs, A and B. That's some measure, for example, the absolute value of the moods, and then it computes the probability, and it's a coin flip that's weighted to get the probability of A over A plus B. So the absolute value of the mood over the sum would be the probability of the first one, and 1 minus that would be the probability of the second one. And what's really nice about the probabilistic having this coin flip neuron in our algorithm, in our model, is that we have this theorem that chunks get into short-term memory in proportion to their importance, depending on how we are measuring importance. In this case was absolute value of the mood. And what's nice corollary to that is that the processor location is independent of whether the processor gets its chunk into short-term memory is independent of its location. Another property is that all processors have some probability of getting their chunks into short-term memory. So it's not one versus all, but everybody has some chance. Even those that are lurking in the background have some chance of getting into short-term memory. And here's the formal theorem. I'm just going to read it to you, but we have let F be any additive competition function, which is a formal notion that we have. Then for all processors P and time T, the probability that P wins the competition, in other words, it gets its chunk into short-term memory, will be the F value of the chunk over the sum of the F values of all chunks that were put in at the same time. Okay. So once a chunk gets into short-term memory, and here I only have 4 of the parameters here, it gets immediately broadcast in one time unit down to all long-term memory processors. So again, in our model, we don't want to differentiate. We just want all of our processors to get the chunk that was in short-term memory very quickly. And if you notice, the uptree competition is, slower than, it's because it's a competition than the broadcast, but nevertheless, it doesn't take very long. There's a little delay in time, and in fact, that's really interesting because the neuroscientists have found that there's a slight delay in time for your ideas that are churning in your unconscious processors to get into consciousness. And a similar phenomena happens here in our model. But the broadcast is very fast. And the broadcast has this nice feature of giving feedback to our sleeping experts or our long-term memory processors. Our long-term memory processors actually give predictions. Every time they put something into the competition, that's a prediction of what they're thinking about. or when they actually send something to the external output, that's a prediction. And they need to get feedback so that they know whether their predictions were good or bad or whatever. So this is a major part of the feedback that they get is from the broadcast from short-term memory. And this is where we actually utilize Avram Blum's work on sleeping experts algorithm. In fact, this is when we told Avram we were working on this and we told him a little bit about the model, he says, oh, your long-term memory, your unconscious processors, oh, they're my sleeping experts. And in fact, I have an algorithm that you probably want to use. And what this algorithm does, which is really excellent, there are many variations of the algorithm, is that some processors put chunks, are very egotistical, and they give very high weights to they think they're godlike, and they give very high weights to their chunks. And sometimes those chunks are wrong, probably very often. And what the sleeping expert algorithm will do is it will lower the weights for those egotistical processors. On the other hand, as you know in yourselves, that sometimes you're very timid. You have a very, very good idea, but you're kind of timid, and you may give low weight to that to that idea. And so it doesn't have, it's a good idea, but it doesn't have a chance of getting into short-term memory. And after a while, you'll find out about that, and the sleeping experts algorithm will boost your weight. So it lowers the weights of egotistical, chunks from egotistical and wrong processors, and it hires the weights for those that might be very smart, very, very good chunks, but a little too timid. Okay, I'm not going to go into detail. There are papers on this, and our monograph will have these things in detail. We have a little indication in our paper that's in archive on sleeping experts. Okay, so let me give you I'd like to give you a sort of the overview of the conscious Turing machine dynamics now that we have enough information. So we have inputs coming in from the external world, the outer world, and the inputs will go to several, from the sensors to different processors. Once these inputs come in, at every moment in time, the long-term memory processors are putting chunks into the competition, and possibly the fear processor really is reacting very strongly to this input, and its chunk gets into short-term memory. Fear of -10 gets into short-term memory, and as soon as it gets into short-term memory, that chunk is broadcast to all long-term memory processors. And in particular, the inner speech or the speech processor decides it wants to react to this information it just got of fear, very high fear with a mood of -10. And it wants to react to that. So it sends an output to its external world, and it's activating its screaming mechanism and really saying, hey, this is very fearful. So this is the kind of dynamic that's going on within our conscious Turing machine, and also in turn there's a dynamic going on in terms of all the all the long-term memory processors internally, in terms of learning and so forth from the feedback it's getting. You might notice that processor B reacted to processors A. So processor A was fear here. It sent up a chunk of fear, very fearful. Inner speech processor B reacted to that. And so whenever long-term memory processor A links up to, whenever processor B answers A's call, processor A will link up to processor B. In fact, we have these bi-directional links happening. And this is the Hebbian principle that neurons that fire together wire together. Okay, so A links up to B when B answers A's call. And in fact, this happens when B's answer is what A thinks is a good answer, and over time, more and more links will go between A and B and other processors. And linking is very important because it enables conscious processing to become unconscious. So processing before that we said it went from A up to short-term memory down to B reacted. In the future, A might go directly to B with its chunk, bypassing short-term memory. And indeed, this was what happening when you sort of remembered her name. It was your long-term memory processors interacting with each other via links. It's what happened to Poincaré when his long-term memory processors were interacting via links that had formed over time between different processors. And then when an answer happens, that when they saw that connection, they all got it up into short-term memory. Okay, so now I've given you a cartoon version of our conscious Turing machine, and this is sort of like the cartoon version of the Turing machine that you've seen with a state there and a tape and so forth. But we can formally define the CTM as a 7-tuple. Turing machine is also defined often as a 7-tuple, coincidentally. As STM, the formal definition, LTM, down tree, up tree, links, input, output. There's formal definitions for all of those. We will formally define the chunk that processors put into competition, address, time, gist, weight, intensity, and mood. And we have also what we call predictive dynamics, and that's also part of our CTM, where we have predictions where the long-term memory processors, as I said, are predicting when they put chunks into the competition for short-term memory to get on stage, when they send information to the external world, and also now through links. Those are their predictions. And they get feedback now from the broadcast, from the external inputs, and also now from links. And internally in each of these processes, there's a lot of learning going on. One of the major parts is the sleeping experts algorithms. There are 3 very important processors that will come up when we discuss whether the CTM has the feeling that it's conscious. And this is the inner vision, inner speech, and model of the world processors. But first, let me formally define what we mean in our model to be conscious. So we formally define the chunk that gets into short-term memory to be the conscious content of our conscious Turing machine at the time it gets in. And we say that consciousness in our conscious Turing machine is the awareness, in other words, the reception by all long-term memory processors of the conscious content of CTM. In other words, when that chunk gets broadcast down, then we say that our conscious Turing machine is conscious of that that chunk. So these are definitions. We see that the constant activity of chunks competing to get into STM and then broadcasting down to the long-term memory processors, competing to get into short-term memory, our stage, and then broadcast down to the long-term memory processors, unconscious processors, creates a kind of stream of consciousness. And this is sort of what James was talking about a century ago, the stream of consciousness. The reasonableness of our definition of consciousness lies in the number of concepts that the model explains easily and naturally. And I'm going to give you 3 examples that have something to do with sight, but the reasons for these, the phenomena, are somewhat different, but can be explained at a very, very high level in our conscious Turing machine. So I'm going to start with blind sight. And here is, you see this room, that very cluttered room, looks like an obstacle course. There's a gentleman sitting on the right on the sofa here, and he's asked to go to the other room that's here on the left. Perhaps the food is being served in the other room. But this gentleman says, "I can't see." Nevertheless, he gets up, walks to the door on the other side of the room, and avoids obstacles. So what's going on? And so let me again give you a very high level explanation here. So his getting input from the external world through the sensor into the vision processor. And the vision processor is working properly, and it sends a message to the walk actuator, and the guy gets up and walks across the room. But the connection to the short-term memory from the vision processor is either non-existent or broken. And so without vision processor having access to short-term memory, he has no conscious sense that he can see. So that is our high-level explanation of blind sight. So here's another example. It's called inattentional blindness. And you may have seen this film. It's a pretty famous film here. Viewers of this film were asked to count how many times white-shirted players pass the ball. So we have a group of students, and they're passing a basketball around, and some have white shirts and some have black shirts. And people generally viewing this film will have a pretty good count of how many times. It's either 11 or 12, something like that. So here's a little bit more of the film. But did you see the gorilla? So if you've seen this before, you may have seen the gorilla, but most people watching the film do not see the gorilla, even though here in one of the things the gorilla is right there in the center and even pumping its chest. So what's going on here? Well, what's going on is when we are given a task to look for something, we put higher weights on that task. Okay, so our gist is going to put high weights on look for white, and it's going to put lower weights on things that we're not particularly interested in looking at. So it's going to put lower weights on the gist that says look for black, because we're really interested in white. And this is what's really happening in inattentional blindness here. There's another film that's also quite popular, and it's called Who Done It? And here is a scene, starts off with a scene, and here's this inspector coming into the scene here, and he sees this guy who's obviously looks kind of dead on the floor, and he says, "Clearly somebody in this room murdered Lord Smythe. Each of you tell me your whereabouts." And so the maid says, "I was polishing the brass in the master bedroom." And the butler says, "I was buttering his lordship's scones." And Lady Smythe says, "I was planting my petunias in the, And the detective says, "Constable, arrest Lady Smythe." And she says, but how'd you know?" And he says, "Madam, as any horticulture will tell you, one does not plant petunias until the spring." So that's the solving of that mystery, but there's actually a bigger mystery for us, which is called change blindness. And this is the picture at the beginning of the film, and this is the picture I just showed you at the end of the film. And you might notice there have been some changes here. In fact, the biggest one here that we notice is that the detective's coat has gone from dark color to white. Okay, and we can notice that the flower pot and flowers have changed. And then I might notice that this dead guy has changed his clothes, and his knee is now up, and it wasn't before. And the bear has changed to a coat of arms, and a bust on the left has just appeared, and in fact the tapestry has changed to a picture. And there are many, many more. Actually, the butler here has a rolling pin that's changed to a candlestick. And you could find in these pictures many, many, many other changes. So what's going on? Why didn't we see the many changes? And the reason for that, again, a high-level reason from the CTM, is that we've given these two scenes the same gist. The gist is a very compact description of the scene. There's a scene in the living room of a mansion with a maid, a detective, and a man laid out on the floor. So that that gist equally describes the first scene and the final scene. And so the gist is really the same. That's important for us here. So we've used the same gist in both cases. Also, is a very clever way of filming this movie. We don't see any flickers. It goes from one scene to seeing the maid, maybe seeing some of the other people, and then it'll finally end up with this final scene. So there's no flicker to really let us know that a change has happened at all. So our gist remains the same, that same gist. So we don't know this. So again, the reasonableness of our model, I wanted to say, explains, at least in this, three things that have to do with sight, and they have different reasons. So the blind side is explained by broken, in the CTM at a high level, by broken branches from the processor that's important to the short-term memory. So it can't get its information of visions into consciousness, so it's not conscious. Inattentional blindness, again, is the fact that chunks in the CTM are giving weights to what they consider more weights to things that they consider very important, and lower weights to things that they consider less important. High weights to look for white shirts, low weights to look for anything black. So it doesn't see the, we don't tend to see the gorilla there. And change blindness, again, has to do with just chunks, but a different part of the chunk. In the change blindness, it had used the same gist to explain the first scene and the last scene. And the gist gave us the overview, but it did not give us the details, the details, because that didn't seem to be as important to the film. Okay. So right now we know that the CTM is consciously aware by definition of the conscious content of short-term memory that is broadcast to the long-term memory processor. But this definition does not explain what generates the feeling of consciousness, why CTM might have the feeling that it is consciousness. So this brings us to the big question, will the CTM have the feeling that it is conscious? Yes or no? Well, we believe that yes, but how do we prove that CTM feels it's conscious? We don't. But we give some arguments. We argue that the feeling of consciousness in the conscious Turing machine is a consequence in part of the extraordinary expressive power of the brainish language, certain special processors, which I'll talk about in a second, and the predictive dynamics, and some minimal ability to think. So what I'd like to do is just talk about some of the special processors. We've already talked a little bit about the expressive power of brainish, and that's really very, very important. And they come into these special processors as well. Okay, so we have an inner speech processor that does planning, forecasting, etc., that translates all speech in short-term memory brainish into the inner speech that's very similar to what one hears from the external world. And the gists of inner speech are nearly indistinguishable from the gists of outer speech, the gists that are created by the input maps. And in humans, sometimes inner speech sounds so much like outer speech that this can be difficult to ascertain, and this happens often in the illness of schizophrenia, where it's hard to distinguish between inner and outer. But because they're close, we're saying that's one of the things that gives us the feeling of consciousness. And then the inner vision or inner sensation processes help translate the all images and sensors in a short-term memory brainish into sketches akin to what the mind's eye sees and senses in dreams. So the gist of inner visions enable CTM to create the inner images that CTM uses to generate imaginings or dreams, and the gists of inner visions are barely distinguishable from the gists of outer visions. And again, our inner visions of dreams are very similar to our outer visions, and one of the ways our bodies protect us against this, they make dreams very hard to remember. If we remembered dreams very clearly all the time, we would be very hard to distinguish between reality and dreams. And then thirdly, the collection of model of the world processors. So we have inner speech, inner vision, inner sensation, and now model of the world. And this model of the world processors makes models of the world, and it's used for distinguishing self from not self in those worlds, and for predicting actions of self and non-self in those worlds. And let me see, I'm not sure if I can do this, of getting you this baby who's actually, I can't do this here, looks like I can't, who's actually looking at one foot and actually seeing it can move it, and it's distinguishing that's part of self, and it's trying to learn from it to look at its left leg and does not. And the model of world helps for planning actions in the environment. It has a model of the environment and for making maps. So we know that reduced functioning of these processors may create a reduced sense of consciousness. For example, Jill Bolte Taylor in her book, My Stroke of Insight, describes her own diminished state of consciousness following a stroke that disabled her inner and outer speech centers. So we now look at the CTM from the point of view of the model of the world processor. It is aware of both the inner world of imaginings and dreams and the outer world, hardly distinguishing between the outer and inner languages and sensations. It tags, so here we have the inner world and the outer world, there's images in there, and it's in the model of world processor. It tags information. So here it's tagging information, seeing snow outside in the outer world. The CTM, it tags itself. There's a picture of me, and there's a cartoon of me, and there's a dreams of a couple flying. Manuel said to me when he saw this, he says, "Oh, you're making it too personal." And I said, "Well, you know, our CTM is really only interactive with you and me, so that's probably all it knows right now." It views the CTM as a whole that is conscious. And so it labels the CTM as self and conscious. The view that CTM as a whole is conscious, as normally understood, is a consequence and part of the fact the model of the world processors views the CTM in its model of the world as conscious. So here we have it's viewing itself and the CTM as conscious in its model of the world. So from the outside, outside of CTM, we see that something about CTM is conscious. It cannot be the model of the world processor or any other processors, since processors are just machines running algorithms. The view that CTM as a whole is consciously as normally understood is a consequence in part of the fact that the model of the world processors views CTM in its model of the world as conscious. So in its model of the world, it's viewing its model of CTM as conscious. It's doing many things that we view as conscious. So from the outside world, it is viewing CTM as conscious. Even though many of the mechanisms, and in fact all of the mechanisms, are just processors, just machines running algorithms. But it's this mechanism of the inner speech, the inner vision, inner sensations, and this model of the world in CTM that is really accounting for its feeling, we believe, of consciousness. I don't have time to go into Gordon Gallup's mirror test, but it's not a perfect test, but his test of self-awareness captures at least three requirements of our requirements for consciousness: the model of world for distinguishing self from not self, inner dialogue for planning, and the ability to think, including motivation and energy. And I'm not going to go through these, but one might ask, do elephants pass the mirror test for self-awareness? And you put a marker on the elephant's above its eye. It goes over to the mirror, very large mirror, and it sees the marker, and it really tries then to wipe it off. It knows It's not part of self. There are other very tiny animals that the cleaner fish, Wasserfish, also passes the mirror test. Also, a species of ant, American ants, pass, and even young children of 2 or 3. I apparently can't do this video, but here's a child that actually looks at itself in the mirror, doesn't quite know what to believe, goes behind the mirror and goes back and forth trying to figure out. So if we wanted a measure for consciousness, this isn't a perfect test, but it's not a bad test either. So I want to end my talk with the extended mind of Andy Clark and David Chalmers. They talk about that our mind is not just what's in our heads, but it's extended. It's the people we talk to, the books we learn from, the libraries we go to, all of the kinds of inputs that we have that make up our mind. And Elon Musk went one step further on this, and he embedded a Neuralink in Gertrude the pig, which brings in many other sensors into Gertrude. And so we also talk about the extended conscious Turing machine. And what we do with our Turing machine is we allow our Turing machine to have access to all the best technology that's available, to AlphaGo, to Wolfram Alpha, to Siri, to Google, and all of that. And we allow that to be part of our long-term memory processors. So this, in fact, will be our model of the extended conscious Turing machine. And finally, our view of consciousness, again, it's the property of all properly organized computing systems, whether made of flesh and blood or metal and silicon. And our thesis is the architecture of these systems, its key processors that are able to communicate thoughts, plan images, and sensations in an expressive inner language, and the dynamics of prediction, feedback, and learning that makes them conscious. And as I said, we have a preprint up on archive, which you can get, and this is the end. And I thank you very much for this invitation, and again, congratulations on your Jubilee, your Golden Jubilee. Thank you.
Thank you, Professor Lenore Blum, for the excellent talk. I request everybody to please use the raise hand feature if you would like to ask questions. And if you're facing problems with the mic, feel free to type it out in chat and we will relay it to the speaker.
Yeah, and I'm going to eliminate my screen sharing so you don't have to